Hi, my name is Michael Poza. I'm an assistant professor here at the GRASP Lab at UPenn. I'm going to talk about some of our recent work on multi-contact robotics, covering a few different topics today, from modeling to control, as well as some of our latest work on deep learning. It should come as no surprise to attendees of this workshop that impacts are becoming increasingly prevalent in robotics. I think this is really largely due to increases in capabilities, particularly on the locomotion side, when it comes to performing very dynamic human-like motion, whether that's running, jumping, work we've seen from Boston Dynamics, agility, and others. I would say the manipulation side, we're still a little ways away from this, right? Here is Iron Chef Morimoto chopping some vegetables, and I don't think our robots are quite there yet. But again, as they grow in capability, as we try to push them towards the type of dynamic behaviors they're really going to need to succeed in complex and human-like environments, they're going to need to be faster, and they're going to need to be able to deal with impacts. So today I'm going to talk about our work in a few different areas. We'll start with some work on control, and particularly how to handle impacts in the feedback setting. Talk about modeling, specifically focusing on impacts and how they can generate non-unique events, and then conclude with a discussion of learning and contact. Okay, so let's start with jumping here. So this is our Cassie biped in the lab, jumping and landing, shown here in slow motion. And a pretty traditional, rigid body hybrid strategy would look something like this, right? You'd plan for a few different phases, a crouch, a flight, and a landing phase. The plane would have both feet landing at the same time. It'd have some kind of instantaneous inelastic impact event. And then the controller would switch, right, between modes from crouch to flight to land. And it would do so by detecting when these mode changes occur and switching its control strategy. Now, all of these sort of assume that impacts resolve instantaneously. And we can look at the data from jumping here, and we can see that's not quite the case. So this is a plot of velocity versus time, where the impact starts at 0. And you can see it resolves fully in, let's say, 10 to 20 milliseconds, depending which joint you look at, which is pretty fast, but not instantaneous. And during that period, the velocity is changing very, very quickly. Our ability to get useful measurements, say, out of our IMU is pretty limited during these high force periods. And even our joint velocities themselves, maybe those measurements aren't entirely trustworthy because they come from finite differencing and filtering. So what's going on here? Well, we can think about this standard rigid body model, which has been mapped from pre-impact V minus to post-impact V plus using some sort of impact law. Particularly, we have some kind of impulse of force, capital lambda here. Okay, and we jump from we have sort of kind of our planned trajectory in going from red to blue. Now, in reality, this takes a little bit of time. Say somewhere on the order of 10 to 20 milliseconds. And during that time, our velocity is somewhere in between. Okay, not quite sure where, and again, this is a cartoon of high-dimensional space. But if we're going to do feedback, right, we need a nominal trajectory to track, and it's not really clear in this window what our nominal trajectory should be, right? If we pick the red or we pick the blue, even with appropriate extensions in time, we're going to get a large tracking error, and then our controller might multiply that tracking error by a gain and end up with a large control input. Which is typically not something you really want, right? And in fact, even though this window is so small, this large input here, which is associated with attempting to track something unreasonable, can actually destabilize the system. Okay, so this is a pretty bad idea in practice to try to instantaneously switch references, particularly when the impact is in the process of resolving. And so these are brief periods of time where there's a lot of uncertainty and sensing is pretty limited. So what should we do? One common strategy that people use, right, that you may be thinking of yourself, is to use some sort of lower gains, right? Drop your gains during this period. It's high uncertainty, so just reduce control efforts. Or maybe you would take the pre-impact controller and the post-impact controller, and you'd blend them together with some sort of weighting mechanism. And these are very reasonable heuristic-driven approaches that work pretty well in practice. But we've been trying to think more carefully about why these are good controllers and why people use them, and can we generalize this to some extent? There's actually some really nice work last year from Gong and Grizzle out at Michigan, where they realized that angular momentum was an interesting quantity here, because angular momentum is constant through an impact event, angular momentum about the contact point, right? And therefore regulating angular momentum instead of, say, joint trajectories might be a good idea. Okay, can we take that idea and we generalize that? Because we want to maintain some control authority. So just dropping gains, for instance, or only regulating a single scalar value, angular momentum, means we don't have a lot of control authority left over, right? We may still want to apply feedback in this window, but just useful feedback. Okay, so our insight here is that while feedback on the velocity that's changing really rapidly is brittle, right, and it's subject to error, the entire velocity is not changing, right? Just like angular momentum is conserved, there's actually an entire subspace of joint velocities that are invariant during an impact event. So we've labeled this the impact-invariant subspace. It's a linear subspace of velocities that are essentially unaffected by impulses that you might apply. So if you look at the span of m inverse j transpose lambda, assuming we're sort of somewhere mid-impact, we don't know what impulse has been applied so far, we don't know what impulse is going to apply, there's still a subset of velocities that are unaffected by this, and that's the space we want to do control on. Okay, so looking back at our Cassie jumping data here, we have the aggregated data over a number of different trials here on the left, again with these rapid changes in velocity during impacts. But then if we form this projection, okay, if we project on this impact-invariant subspace, what we get is a set of velocities that are relatively constant during this window. And this is nice because this is a space now where we can do control, and we're not going to be subject to that high uncertainty that's occurring in the rest of the state space during landing. Okay, so our idea here, this impact-invariant control idea, and this is worked on really by Will Yang in my lab, and published here at IROS. I encourage you to check that out. Is to project the error onto this impact-invariant subspace, and you can do this for joint feedback control, PID control for your joints. You can also do this for your favorite QP-based controller, whether that's some form of operational space control or output feedback. Really, this is a very simple projection you can implement in your code today, and I think you'll see an impact, no pun intended. Okay, so we did a couple of simulation studies first here. Here looking at jumping onto a platform where we vary the height of the platform, essentially changing the time of the impact without letting the controller know a priori about this. And what we see is that the impact-invariant controller is much more robust empirically to changes in ground height. And in particular, it dramatically cuts down this spike in control effort you see with the default controller. Right, where the impactor is resolving and the mode detection is tricky and flawed. All right, so we cut down this brief high force period, which is not doing anything useful and is in fact actually destabilizing the system. Okay, we do this on the real system as well. So here's a side-by-side shot of Cassie jumping and landing, both with and without the impact-invariant projection. And again, from the empirical results, we see that these peaks in force are cut down significantly, and in fact, if you focus here on the hips as it's landing, it'll play once more again in slow motion. Without the impact-invariant connection, there's a lot of vibrations, a lot of oscillations that are being induced by our control policy doing the wrong thing during this window. So again, a subtle change to your control strategy, but one that you could implement today, and I think that would pay dividends. Okay, so that was all kind of from this perspective that impacts are these high uncertainty periods of time, and we should cut down on our control if we think it's going to do the wrong thing. Now, of course, we could also incorporate sensing in here, right? So if we bring in tactile sensing, how can that enable us to design better control policies? And a common strategy here might be to say use the tactile sensing to identify the mode switch, and I think that's a reasonable starting point, but it's not going to get us all the way. And so we'd really like to take feedback beyond just mode detection and switching and incorporate measured forces into a contact-aware control policy. Okay, we're going to take a very simple approach here. We want to take the forces that we measure, these lambdas, and push them directly in our control policy. So we have some policy u of x comma lambda, and now all the hybrid mode-dependent structure in our controller is actually embedded via this measurement of lambda itself, right? So u doesn't switch directly via mode detection; it switches implicitly by measuring the contact force. What I really like about this structure, okay, and here we use actually a linear policy in x and lambda. What I really like about the structure, though, is it's very easy to implement. Right? You don't have to do mode detection. You don't have to have thresholds and these heuristic-driven approaches. All you do is you measure your forces, you multiply them by gains, and now you have a control policy. Okay? We're going to apply this to systems that have soft contacts, although I think you'll see in the video that soft here deserves the air quotes because we can actually capture pretty stiff rapid impact events, and we're going to use something called linear complementary systems as our governing framework. I encourage you to check out the paper. This was at last year's ICRA with the hardware results here currently under review. And what we do here is we design control policies. This is offline. It takes seconds to minutes here by solving a bilinear matrix inequality where we find a controller and a corresponding Lyapunov function to guarantee stability of the linear complementarity system. Okay. Scales really nicely. I think that's a big advantage here versus something that's hybrid. Fundamentally, we can go up to something like 10 contacts or about 1,000 different modes. And do this on hardware as well, right? Very easy to implement on hardware. So this is a cart pull system, which has been modified to have these two walls on the side. Notice that they're soft, right? There's foam padding, but the impact events are still pretty violent. And the failure controllers, say LQR when it's failing, is quite violent. And what the controller does is it uses force measurements during these impact periods to feed into its control policy, and is remarkably robust in practice. I think it succeeded almost every time in hardware, despite linearization and modeling uncertainty. Whereas control policies like LQR that are not contact-aware really struggled in the same domain, right? Without understanding that these contacts are going to occur, obviously, you're putting yourself at a big disadvantage. And here, our feedback is directly just force fed into the control strategy, synthesized offline with optimization. Okay, moving on from control, but sticking on sort of these principal models, I want to think about non-uniqueness here in impact. So as an extreme case, we can imagine something like a pool break. Very, very hard to predict, essentially impossible to predict where the balls are going to go, even from a high-speed understanding of initial conditions. It really kind of depends on which balls are closer to which other ones and which impacts are going to occur first versus second versus simultaneously, and so on. So these multi-impact settings, where again, this is an extreme example, but they occur regularly in robotics, things like landing with 2 feet, things like multi-contact manipulation, where you're touching an object in one place and then bringing another finger into contact, all turn into non-uniqueness if you use a rigid body model. Okay, so this chaotic nature is expressed as non-uniqueness from rigidity. But this is something that's essentially ignored by most simulation and planning, right? A simulator chooses one solution to present to you. A planner is often optimistic in which solution it picks from that set, if it even understands that a set is possible. And the result here is that the feedback controller has to compensate at the end of the day, right? You might have an impact event in practice where you plan for something to occur, something else occurred entirely, and we as engineers probably sort of chalk that up to just impacts being challenging to model and predict. But really, what's going on under the hood, at least we theorize, is that there's this non-uniqueness occurring and this highly chaotic nature. And in fact, if we could express this or capture this better, right, describe the set of possible outcomes, I think we could therefore design better controllers or design better plans as a result. Okay? And really, what this comes down to is the fact that impacts are going to resolve in some unknown ordering or even partial ordering, where one impact may partially resolve and another impact may begin simultaneously. Okay, so what are we going to do here to try to describe this set? I'm not going to go into the full details here today. I encourage you to check out the paper from RSS a couple of years ago or our journal version currently under review. Essentially, we're going to write down a differential inclusion, which says we have the derivative of our state is included in some sort of set. Okay, and this set captures the fact that the impulsive forces during an impact event at different contact points can grow at arbitrary rates, assuming they're impacting. We're still going to satisfy Coulomb friction, and we're going to have some termination criteria when we complete. We can take this impact law now, this set-valued impact law, we can build it into a full differential inclusion for both continuous time and impact resolution. And despite the fact that differential inclusions are sort of known to be a little bit nasty, we can prove that solutions will always exist under some modest conditions, that this prevents penetration, and in fact it generalizes standard methods, whether it's a hybrid method or an LCP-based model. So now we have a mathematical framework for describing non-uniqueness, and in fact we can wrap this now into a sampling-based simulator, where we can sample from the inclusion and simulate to do things like compute post-impact sets. So if I have a simultaneous impact event or a multi-impact event, I can actually go and calculate the set of possible outcomes, right? And so now that we have that set, we could do things like include it in our analysis for robustness, use it for verification, build it into our planner, so maybe our planner avoids these void situations where a large number of outcomes is potentially possible. Okay. with the remaining time here, about half the talk, I want to talk about learning now. So, we've really focused so far on the challenges that are arising from physics-based models, things like uniqueness, as well as the challenges in control. So, is one solution just to collect a bunch of data and use our favorite deep learning methods? Okay, so just to frame this more concretely, let's focus on a model learning problem here, where we're given some set of trajectories, some data of motion. Okay, so here is a SE3 pose in time, showing one trajectory of some data. And I think all of us here could look at this and have some idea, not imperfect perhaps, but some idea of what's going on. There's some kind of impact event. It bounces, maybe it maybe hits once and then again, and then maybe maybe 2 or 3 times total. There's some kind of sliding, it looks like it's going on at the very end here, and then it comes to rest. Okay, so we have some idea what's happening here. We're not totally sure what shape this object is, but given this information, we as humans could do a reasonable job of inferring what's occurred. Okay, as an even simpler example, imagine this set of this bouncing ball here shown on the upper right. Again, I think we can all look at this and figure out what's going on here. This bouncing ball is hitting some kind of flattish surface and rebounding off of it. Okay, not too hard. But for learning, this is actually a really hard problem. And the reason it's hard is because deep networks are inherently biased via regularization to try to find simple explanations of the data. So they're going to try to find some simple function f, which explains the observed motion. And the observed motion, even for this bouncing ball, this 1D particle, okay, is not simple. If you think about the mapping from current state to next state for a discrete time setting, this bounce exhibits as the sharp discontinuity that occurs in state space. And it's really important to get that right, because if you get the bounce wrong, you're going to get everything wrong at the end of the day, right? This is a small region of state space where this occurs, right? Height very close to 0, velocity negative. But it's very important to get it right, right? It is sort of the key feature of the key behavior of the system is that it bounces. That if you attempt to smooth over this discontinuity or otherwise approximate it, I think you're going to run into real trouble with predictive power, as we'll see in a little bit. Okay, so the main kind of takeaway, I think, from this section, and we're going to dive into this in more detail, is that data-driven methods really need to be tailored to stiffness. Okay, imposing artificial smoothing via regularization is a flawed idea, even though it is I think the most common way learning is thrown at these problems. I'm going to give another toy example here and think about friction. So I've written up a discrete time friction law up on the top. It's not super important to get into those details, but essentially this is a high school physics experiment that you probably have run, right? We're going to try to identify the coefficient of friction, and we're going to do it from a single data point that's sliding. Okay, so I've measured the delta V, the force essentially, and I want to determine, let's say I know the normal force, and I just want to determine the frictional force. So what does delta V look like as a function of friction? Well, if friction is very, very high, then your model is going to predict sticking, and so delta V is 0. But if friction is lower, in this case below around 0.47, then the object is sliding, and there's this piecewise linear relationship between mu and delta V. We have our single data point here in red, which says our coefficient of friction is 0.2. Okay, you've probably done this experiment in some form or another in a physics class, and if you haven't, you can imagine how you might conduct this and hopefully measure coefficient of friction. So what happens if we take this experiment and we construct a loss function out of it? So our loss function here is going to be the error in prediction, essentially the observed delta V versus the predicted delta V. So now we have error here squared as a function of mu. We get this nice quadratic shape here on the left, but we also have this big flat region on the right, which says if your value for mu is sufficiently high, then in fact the gradient of the loss with respect to mu is 0, because you're always predicting sticking. And you can see already how this might become a problem for something like gradient descent, where you have these large regions with 0 gradient, and our places where our learning might get stuck. To take a similar toy problem, let's imagine we're just trying to learn a step function here, and we have a collection of noisy data, and we're just trying to learn the location of the step. Well, our loss here, as a function of the position of the step, Again, it has the global minima in the right spot around theta equals to 0, but this is a very nasty loss landscape, right? It's not differentiable almost everywhere. It has this very sharp valley right at the global minima, and you can imagine now that doing this in very high dimensions, your gradient descent or your stochastic gradient descent could really struggle to find the global minima here, even for what looks like, relatively nice data. We as humans would have no trouble identifying the step is at 0 here, given this data set. Okay, so we're going to perform a case study here. This is work also actually published at IROS, done by Mihir Parmar and Matthew Halm, where we're going to look at stiffness, and we're going to make 3 hypotheses that we're going to check here. One is that stiffness inherently creates chaos. Okay, so something like a bouncing cube here shown on the left is tricky to model, period, right? If I have noisy data, and even an Oracle model, I'm still going to have some error as I roll it out. This goes to the fact that rolling dice is complicated. It's a chaotic behavior. Nothing we can do about this. Okay, just inherent to the problem. We're also going to try to analyze whether stiffness hampers training. Okay, whether gradient descent, this goes back to the slide I just showed, whether gradient descent is going to struggle here to train on very stiff models. And then lastly, going to analyze the fact that stiffness conflicts with deep learning inductive bias, right? So this is inductive bias via regularization, that the underlying function to describe the data should be smooth and low Lipschitz, when in fact it's not smooth or low Lipschitz. Okay. And to do this, we're going to take this cube toss problem. We're going to train on a few different values of stiffness. We're going to use recursive neural networks here because they seem to perform the best using LSTM. And those 3 values for stiffness are what we're going to call low, medium, and stiff. I'm showing you medium here just to give some sense of the scale. Stiff is real realistic looking, right? Have no real visible penetration. And soft is very, very soft. Okay, so medium is okay. You can see although it kind of sinks into the ground quite a bit. Soft is very, very soft, and stiff is realistic. And to analyze these hypotheses, we're going to look at our testing error and break it down in a few different ways. So one, we'll look at the Oracle. I'm not going to show those results today, but they show what we kind of expect, which is that, yes, stiffer things are harder to predict even with an Oracle, but that the Oracle error is not sufficient alone to show the result, to explain the results. Okay. We'll look at the error between the training error relative to the Oracle error. This is to answer our second question here about the challenges in training, and then we'll look at generalization error finally to see how well our biases are matching up with the underlying data set. Okay. I'm going to use Mojoka to do this, just because that seems to be a popular tool from the SimDebril and RL communities, and we're going to vary stiffness by varying a single parameter. Okay. And I want to stress that we've made this learning problem as easy as possible. So we've tried very, very hard to optimize hyperparameters. We've optimized them individually over trials. We're only learning single-step predictions. We have no distribution shift between test and training data. Again, this is as easy as we can make it for a learning problem. And what we see is that universally, no surprise really to people who think about this from the physics side, but universally, stiffness is a problem for learning. And in fact, it causes orders of magnitude more error across the board. Okay, so for training error in particular, this is really just, can you memorize the data set, right? Something you think learning would be quite good at. And again, we've done this a lot, right? That I feel pretty confident that these numbers are real and not the result of some kind of training error in setting up the problem. Training error on the stiff system shown in blue, it's just worse. It's hard to train, hard to optimize these data sets. And I think this goes back to this very nasty optimization landscape that I was cartooning before. And we can also look at generalization error, where in many ways the problem is worse. You can see even with lots of data set, if you're training on stiff data, the generalization error hardly goes down as the data set grows to the hundreds of thousands of trajectories. Now, if you're working on a soft problem, right, it's pretty easy. It works pretty well. Like deep learning works great on soft contact. But if you're trying to take sim to real for a stiff system, or you're trying to perform RL in simulation and hope it works on the real world, if your real world is stiff and you're training on a soft simulator, I would be very skeptical of those results. I think that's sort of one takeaway here is that the stiffer the system gets, you see dramatic degradation in performance from deep learning. So hopefully if you're using Majoko, you're cranking up that stiffness to something realistic. Okay, we've also done this on real data. So I'll show some a video here of our best attempt using a neural network to capture real data. And it's okay, right? It gets sort of the position motion roughly correct. It really botches rotation. And has no idea of penetration, so the simulated cube in green goes through the ground, doesn't come to rest on a face, and so on. There's some big qualitative errors here with our prediction from a deep network. Now, instead, what if we build in some physical priors? Or what if we build in some discontinuous structure in particular? I'm going to go into this in detail, but if you build in that structure, you can get performance that looks like this, where now you've captured these qualitative behaviors, right? You come to rest in finite time. You have these sort of very rigid bounces off the surface, and you don't see observable penetration between the simulated cube and the real cube. Okay, so this is what we can achieve, and so then the question is, how do we do that, right? So this is work from Coral last year in 2020 by Sam Frommer and Matt Holm again, where what we're going to do ultimately is build in some discontinuous structure to the learning problem. Okay, so physics-inspired representation, and do that in two different ways. So one is we're not going to try to learn the dynamics directly. Instead, we're going to learn geometry, which implies dynamics, geometry and surface features that generate motion. And the reason for this is that the dynamics are non-smooth, but the geometry is smooth. So we're going to let the learning biases work for us by trying to learn something that we think is nicely regularizable, as opposed to just trying to learn raw dynamics. And then the second thing we're going to do is that even though we have a model that comes out of this, we're actually not going to simulate that model during training. We'll simulate it for things like rollouts, like in the video, but we're not going to simulate during training because simulation is stiff. And instead, we're going to compute a loss function via convex optimization, via bi-level optimization. Okay, before I go into the details of that loss function, just to give the high-level results, we have a couple different ways of parameterizing the system. We can use a polytope, so for kind of very heavily structured geometry, or we can use a deep network. Those are shown in blue and purple here. But either way, we greatly outperform state-of-the-art baselines from kind of end-to-end dynamics learning. We do really well in things like penetration and rotational error comparatively. If we use, let's say, the polytope representation within about 10 training tosses, we've really figured out everything we need to know about this system. So the data efficiency is really remarkable here for learning these very stiff frictional dynamics. So how does this loss function work? So the key problem, again, is that the prediction loss is not differentiable, right? My model of theta here is not differentiable. It's not smooth. And so generating this loss function is a bad idea. Instead, we're going to redesign a loss function for discontinuous dynamics. And one way to think about this is to say that, well, we have a function f here which has very high Lipschitz constants, and so we would like to avoid relying on learning properties that scale with Lipschitz constant. Right? We need to rethink this problem setup. So first, as I said, we're never going to simulate. Okay, simulation. One way to think about that is picks a contact force which matches your model exactly. So we're not going to do that. Instead, we're going to optimize via QP or QCQP over possible forces lambda. Okay, so we're going to, for each data point, we're going to say what force goes with this data point. And that's composed of a couple different terms. So one is that the force we pick should explain the motion. Okay, I'm seeing a transition. What force could plausibly generate that transition from one state to the next? And then also that force should match our model. Maybe not perfectly, because perfectly would be simulation, but a force should match our model roughly, and we have loss functions to soften that, corresponding to things like non-penetration, complementarity, and dissipation. Okay? And the result here is a loss landscape that I think, at least on the toy problems where we can visualize it, it's just beautiful. Okay, it's a nice convex loss landscape for the toy problems, works really well in practice on more high-dimensional problems, and does so by again tailoring this description, this loss, to non-smooth systems. So key takeaways, I think, from today are that I would be very skeptical in general of applying extremely generic approaches to multi-contact robotics, whether that generic approach comes from standard learning methods or a raw hybrid control strategy. I think there's a lot of structure from impacts and from friction that if you incorporate that carefully, you can get controllers or you can get learning algorithms that are maybe as generalizable as they need to be for multi-context systems, but are much more effective, much more tractable, much more scalable. Right? So I think a lot of the questions, a lot of the insight here comes from careful incorporation of these physical priors. There's a lot of work still to be done in this area, though. So I'll highlight a few things that I think are open problems, things that we're working on or not really. So real-time control. This is something we are working on. I think it's a real challenge to take any of these strategies and get them to say real-time model predictive control for a multi-context setting. We have some ideas. We hope we can report on those not too far in the future, but I think this is an open challenge for sure. Scaling the learning, we've shown really nice results on a single object, but doing this for lots of objects, doing this for something like multi-finger manipulation, I think that's in the works, but still have to get there. And then lastly, a lot of these control strategies were based on the fact that impacts and multi-impacts are very hard to capture perfectly, right? But can we understand uncertainty? So can we do something better, so let's say for the impact-aware jumping controller, than turning off gains in certain directions, right? I think if we had an idea of what the uncertainty was like, we could do some kind of more traditional robust control. I want to thank all the students who made this happen, some of whom, whose work I highlighted here, but others who are also doing excellent work, and mention some of the papers, again, that we relate to the work I talked about today. I look forward to the workshop and chatting with you all down the line. Thank you very much.